Hello, in this video we begin our discussion of colligative properties. That is, those properties that depend only on the amount of solute dissolved and not the identity. Properties that we'll discuss include boiling point elevation, freezing point depression, and osmotic pressure. Now, there are some basic assumptions associated with these colligative properties and the equations we're to develop. One is, as noted earlier, that these properties depend only on the amount and not the identity of the solute. We will also note that we will assume that the solute itself is not volatile, so that it has a very low vapor pressure. This might be an example where we dissolve some solid, like salt, in water. We'll note, of course, the solid has a very low vapor pressure. And then finally, we'll make the assumption that the solute does not dissolve in solid solvent. So when the solution freezes, what freezes is only the solvent. The solute remains behind in liquid solution. Again, if you consider a salt water system, when the water freezes into ice, the salt remains behind in the liquid water. So we start with a discussion of freezing point depression. As usual, if we're interested in melting points, of course, we're interested in an equilibrium situation between the solution and the solid. And in this case, since the solid is going to be pure solvent, then we indicate that by the asterisk that we're talking about the pure solvent. And the solution, of course, is a mixture. So we have over here on the left the chemical potential of A in solution at equilibrium is going to be equal to the chemical potential of pure A in the solid. So equating the relationships that we've used before for Raoult's law, we note that the chemical potential of the solution is related to the mole fraction of the solvent in our solution. And so we just substitute that expression that we've discussed in earlier videos, and then we rearrange the equation and solve for the natural log of x sub a. And noting that what we end up with is this difference between the chemical potential of the pure solid and the chemical potential of the pure liquid, which is nothing more than delta G for the process of liquid going to solid, and we refer to that as negative delta G of fusion, because of course when we refer to the delta G of fusion, we're referring to the opposite process here. Now, looking at the temperature dependence then requires that we take the derivative with respect to temperature, and we use the Gibbs-Helmholtz relationship that we developed earlier, and that's given here by this partial derivative being equal to negative delta H over T squared. And again, this is something we derived earlier in the semester. If we note here that in our expression on the previous page, we had delta G over T equal negative R ln of x sub a, then we can make the substitution into this derivative, and we then take the negative delta H over T squared and substitute it into our result, and this is what we have under these circumstances. So we end up with this overall expression. Now, multiplying both sides by dt and integrating, we have this situation here. But we note that the lower limit of the integration corresponds to a mole fraction of 1, which means we're talking about a pure substance A. And of course, if we're talking about pure substance A, then the corresponding temperature is just the melting point of the pure substance A. So evaluating that integral, it's a pretty straightforward integral, ends up with this expression here. And rearranging that in terms of temperature, because what we're trying to determine here is the melting point temperature of the solution relative to the melting point of the pure species. So T again is the melting point of the solution, and T star would be the melting point of the pure solvent. All right, so this gives us a relationship between the melting points based on mole fraction. Now, if you recall back in general chemistry, you learned an expression for freezing point depression that included molality. So how do we make that transition from mole fraction to molality? Well, here it is. So what we're going to do is we're going to start with, of course, our expression for the natural log of x sub a, and relate that to the mole fraction of our solute. And remember, A is the solvent here, so we're relating this now to the mole fraction of the solute in this situation. And then using the definition of mole fraction, we end up with the ratio of the number of moles of solute divided by the total number of moles. And if we have a very dilute solution, of course, what we note is that the number of moles of our solute is much, much smaller than the solvent, and we can make the substitution under those circumstances that the total number of moles is roughly equal to n sub a, and so that gives us this expression here with n sub b over n sub a. So we have this expression now for the natural log, but we still haven't converted it to something that looks like molality. So we go back to the basic definition of molality, which is the number of moles of solute per kilogram of solvent. So in this case we have 1,000 grams instead of a kilogram. And noting that the expression above has the number of moles of solvent, B, divided by the number of moles of, the number of moles of solute, B, divided by the number of moles of solvent, A, then we're going to want to make a substitution. And of course we will note that if we have 1,000 grams of solvent, 1 kilogram of solvent, the number of moles of solvent in 1,000 grams is just given by the mass divided by the molar mass. Simple chemistry, right? So now we have two expressions related to the number of moles of solute, B, to the number of moles and the number of moles of solvent, A, and we can do some simple substitution. Taking the expression related to molality, we can just simply rearrange that to solve for n sub b, and we end up with this expression here for n sub b, and we can then just go ahead and substitute that into our ratio above. We can do the same thing with the number of moles of A and substitute in our ratio above, and we end up with this expression here, which now has molality in it, multiplied by 1,000 grams. Now, of course, the 1,000 grams of our solvent A will cancel out, and we end up with an expression which just has the molality of our solute divided by the molar mass of our solvent. Excuse me, I meant to say that the molar mass of the solvent here is in a denominator of the denominator, so it ends up with a situation where we're going to have the molality of our solute multiplied by the molar mass of our solvent. So this is what we have then after making that substitution. The natural log of the mole fraction of our solvent is roughly equal to the natural log of 1 minus the molality of our solute multiplied by the molar mass of the solvent. Using an approximation that we talked about earlier, we note that, of course, the natural log of 1 plus x is roughly equal to x, and so that means the natural log of 1 minus the molality times the molar mass is roughly equal to this negative molality times the molar mass. And making the substitution into our original equation here, for the natural log of x sub a, again going back to the equation that was derived on a previous slide, we end up with this equation here that relates the melting point of the solution to the melting point of the pure solvent, along with this term here, which has the molality of the solute, and then the molar mass of the solvent and the enthalpy of fusion of the solvent. All right. So then again, rearranging the equation, bringing the 1 over t star over to the left side and doing a little bit of algebra to get these together, we end up with this expression where we have all the temperature terms on the left, and then we have the molality dependence on the right. All right, so continuing with our approximations, we can note that we have this T times T star in the denominator of our previous expression, and noting that these temperature changes are relatively small, we can make the approximation that T is roughly equal to T star, and that means that T times T star is going to be roughly equal to T star squared. Again, remember, T star is the melting point of the pure solid. So again, rearranging our equation based on that, we end up with this expression here, and we note that we have the molality multiplied by a constant. Everything here in this particular term is a constant. The enthalpy of fusion is a constant. The melting point of the pure substance is a constant. The molar mass of the solvent is a constant, and R is a constant. So what we end up with is a constant times the molality of our solute, and we can therefore simplify that, combine all those constant terms into one term, K sub F, which we call the cryoscopic constant, to end up with the general expression, which you saw in general chemistry, that the freezing point depression is equal to negative K sub F times the molality, where K sub F, of course, is equal to these combination of terms. So if you have information about the solvent, its melting point, its molar mass, and its enthalpy of fusion, you can calculate the cryoscopic constant. Note that for water, that cryoscopic constant is equal to 1.86 Kelvin per mole. If we want to do boiling point elevation, the derivation is really almost identical. The only difference is the sign changes because of the nature of the derivation early on, and we end up with an expression for delta T, the elevation in boiling point that occurs when we add solute, with the constant K sub B, and K sub B is given by this set of terms here, where you'll notice a direct connection between the cryoscopic constant. In this case, we substitute the boiling point temperature for the melting point temperature, and we use enthalpy of vaporization instead of enthalpy of fusion. But really the derivation is almost identical for the boiling point elevation. Okay, so now let's move on to discussion of osmosis. In osmosis, what we have is a situation where we talk about diffusion of solvent through a semi-permeable membrane. Here we have a beaker that's containing pure solvent, and in that beaker we have a tube with a semi-permeable membrane at the bottom that allows solvent to migrate in and out. So the solvent can pass through the membrane into the solution, or it can pass out of the solution into the pure area. The point is that the solvent can migrate, but the solute cannot in this situation. So if we look at chemical potentials here, we'll note, of course, that the chemical potential of the solvent in the solution is given by this familiar expression related to Raoult's law, and depending on the mole fraction of the solvent in solution, so whatever that mole fraction might be inside of the solution, we'll note, of course, that because the mole fraction is less than 1, that the chemical potential of A in solution is going to be less than that in the pure solvent, and that, of course, means that since systems move toward a lower chemical potential, that it's going to be natural for the solvent to pass preferentially from the area outside the membrane to the area inside the membrane where the chemical potential is lower. And of course, ultimately, the desire is to achieve equilibrium, desire, of course, being anthropomorphic, but the goal is to achieve equilibrium here where the chemical potentials would be the same. So movement of the solvent from outside to inside is progressing in that direction. All right, so what will happen naturally is that as the solvent moves into the solution, it's going to increase the volume of the solution, and it's going to drive the solution up through the tube to a height, and as it's doing that, of course, it's going to increase the pressure coming down, the pressure based on the sheer weight of the solution. That pressure is going to increase on the solution, and eventually the pressure will increase to the point where the diffusion of the solvent from outside to inside the membrane will stop. So when the pressure reaches the point where diffusion stops, the force pushing down is such that it's equal to the chemical potential. It equalizes the chemical potentials because of that force pushing down, preventing diffusion inside the membrane. That pressure which causes it to stop is referred to as the osmotic pressure. All right, so let's, of course, being physical chemists, derive the equations associated with the osmotic pressure and see how it relates to the concentration of the solute in this situation. So we start with an understanding that, of course, when we reach the osmotic pressure, we are at an equilibrium situation where the chemical potential of the pure solvent outside the membrane is equal to the chemical potential of the solvent inside the membrane. The key difference here being that it's at an elevated pressure. All right, so that when the osmosis stops, that's the situation we have. We have an equilibrium, and these two chemical potentials are the same. All right, so of course, again, using Raoult's law, we note that the chemical potential is indicated on the right, will then, based on mole fraction, be equal to this. And again, this is the same expression we've used before, where we're comparing the chemical potential in solution to that of the pure substance. And then we note, of course, that the chemical potential on the right side of the equation here is at an elevated pressure. So using the pressure dependence of chemical potential, we can split that first term into two terms, where we are talking about the chemical potential here at some pressure P, plus this integral, which shows how the chemical potential depends on pressure. This is something that we've seen before. So we are simply splitting that first term corresponding to the chemical potential at P plus pi into the second term, where second set of terms, the two terms which equate and represent the pressure dependence of the chemical potential. All right, so of course these terms are going to cancel, and we rearrange the equation, so we have an equation relating our simple integral here to the mole fraction of A. And of course, if we assume that the molar volume of the solvent, and remember this is the molar volume of the solvent that we're talking about, the molar volume of the solvent remains constant over this particular pressure range, then that becomes a constant integration, and we end up with the result that we see here after the integration. Then, of course, noting that we've got the mole fraction of the solvent, we can relate that to the mole fraction of the solute as we did earlier. And we end up with our expression here. All right, now, again, one more approximation. Well, not the last one, but we have, again, relating, because x sub b is small, that we can show that natural log 1 minus x sub b is roughly equal to negative x sub b. And we can make that substitution. And then noting, as before, that because the number of moles of B is small, that the total number of moles is roughly equal to the number of moles of A that we have here. And making that substitution for x sub B leads to our expression here that relates the ratio of the number of moles of solute to the number of moles of solvent, relates that to the osmotic pressure pi. All right, so noting that, just rearranging that equation, where we bring n sub A over to the right side, and we have this product n sub A times the molar volume. Well, that's the number of moles of solvent times the molar volume of the solvent, and that's just simply equal to the total volume of the solvent. And again, noting that the number of moles of solute is relatively small, the total volume of the solvent we're going to approximate as the total volume of our solution. So we end up with this expression which relates the number of moles of our solute to the osmotic pressure pi. You'll note, of course, that it looks very much like the ideal gas law, so it should be easy for you to remember. So now we have expressions for the boiling point elevation, the freezing point depression, and the osmotic pressure. All of these expressions are dependent only on the amount of solute and not the identity of the solute. Of course, these correspond to ideal circumstances. There are certainly circumstances where at large enough concentrations of solute where these approximations are not valid. And we may look at some of those in the near future. These colligative properties also allow us to do many interesting experiments. For example, as we will discuss in class, we can use colligative properties to determine the molar mass of an unknown substance. This is particularly useful in biochemistry, where the kinds of molecules that we might be talking about, proteins for example, are relatively large. So by measuring the colligative property of a known mass of this material, we can actually calculate the molar mass of that material. We will, as I mentioned, go through some examples of this in class. So this ends our discussion of colligative properties and ends our discussion of solutions in general. Stay tuned for future discussions on chemical kinetics.